Excellent. All right, so we're talking today about graph databases. And what we'll be doing today is we're talking a little bit about data because you need to know about data before we talk about databases. We're going to discuss some different database types and what basically came before graph databases, what are some other alternatives to them. Then we're going to jump into graph databases themselves, and we're going to do some hands-on exercises as well. We are assuming that you've already know maybe a little bit about data and a little bit about databases, but some of this might be review or it might be new. So again, if I'm going to fast throw up a check, put in a message, and we are off now to get started. So let's get started with data. And there has the obligatory Star Trek reference and Data himself here. And so why do we want to start with data? The first question is, well, what is it? What is data? What kind of data do you have? What kind of data are you working with? And just go ahead and throw in the chat here, maybe what kind of data are you used to working with? What kind of data do you have? Why basically are you interested in graph databases for the data that you've got for your own work? I'll get things started. A lot of the data I work with is a lot of humanities data where we have to take that from, say, texts or say from documents, which aren't really formatted like data. So we have to actually put things into a data format. We've got here publication and grant info tracking. Okay. So lots of like, say, people and lots of bibliography that would go into that. Census data. Yes, there is a ton of census data. That's always a fun one to deal with. All right. Is anyone dealing with more like, say, scientific data or instrumentation data? Pollution, environmental indices. Okay. So all kinds of different data that we have. One thing I want to say, this is a big question we have, is how do we turn data into information? In other words, we have data, we have this stuff, and one of our objectives with it is to really share what it means, right? It's not enough that it sits in our instruments or sits in our indices or like sits in our documents. We want to share this with people. And so one of the important things is how do we do that? How do we make this transformation where we're communicating what our data has? And what kind of rules do we follow for this? In general, we have, ethical rules. We don't want to lie about our data for the most part, right? What are some other rules that we follow? We have formats. Think about the things in your field. Think about what you're trying to accomplish. Think about statistics that you feel comfortable doing. We all have these parameters of data, what it means, how we're displaying it, what rules that we follow. The question here is data a cultural construct? So in other words, is there such thing as raw, pure data that is perfect? Or are we always imparting in some kind of thing into data? Any thoughts on that? Does anyone think that, there is a form of data that is pure and perfect, or are we always doing some kind of rule or some kind of transformation or some kind of thing on our data? I'll say for the humanities, that's basically what we do is complicating things, putting our culture into it, transforming data. What about some of you other people who are looking at data? And if you don't want to share that at the moment, just think about that. What goes in to actually making data, putting it in a form that you use it, and are there judgments? Are there other ideas that have to be followed there? Well, that's going on. The idea is that we have data, but here's the thing about it. Even we have like examples of census data, even people that are using it, who have the same questions and who have the exact same data source, will be constructing something a little bit different. Yeah, good point here from Aaron, that the construction of an index or the construction of what you're looking at is really depending on your priorities. And that's just something to keep in mind as we talk about these data constructs, especially about graph databases, is they're actually designed to deal with this. That deal with these kind of different ideas, deal with these different things about data, because it gives us actually a way to bring in different viewpoints while we're talking about the same conceptual thing, which is really kind of a unique and an interesting way to look at databases. Yes, so good question here. There must be an agreement. Yes, there's going to be agreement, but there can also be disagreement about the data. And so, yeah, this is one of our open questions about when we're thinking about all this. Think about, does your data adhere to it? Does it not? And you'll see what we mean as we move forward a little bit. So let's think about, as we're talking about data and data models, a really brief talk about them. And that, think of the data models that you use and how you basically design applications, or how you design your expression of data, or how, as we said, index it, or how do we sort it, how do we bin it, how do we actually look at it as something, and that this is an extremely subjective and narrative process. You're really putting expressions into your data. And why do I keep bringing this up? Because as you'll see, there's no real correct way to use a database or to use a graph database. But there isn't some kind of, oh, this is the exact way that you must model this at every time. And in fact, you'll find there's a lot of competing ideas about how to model data, even within your own field. And so, while there's not an objectively correct way to model data, there's plenty of incorrect ways and ways to go about it that don't work. And so, if you've heard of these terms, vocabularies and ontologies, these are things that people have gotten together to help describe data. And some are more aligned with some models and some scholarship than others. Now, we're not going to get to a lot of details of these today, because that's a whole workshop topic on its own. But I want to show you a big, scary graph about these, because these are actually really useful when you decide to model or communicate your data, especially within your field. So if you have, say, geospatial data, there's certain ontologies and vocabularies that people have agreed upon to talk about this. So what are these things? And so you may have heard of these terms before. They're a little bit squishy, but the idea is that vocabularies are basically terms used to describe data consistently. So think of them as like a vocabulary would be something like a kind of place type if you're thinking about geospatial things. Maybe it is a kind of animal name. Maybe it's how you describe if you said like a census, how do you describe a block? How do you describe a road? These are basically standard terms that you could use in your data so that it's interoperable with other people. And there's really no logic behind how they link up. It's basically just we're agreeing on using a set kind of language. And this becomes, as we'll see for graph databases, you'll be able to hook up your own data and how you look at things to vocabularies simply by saying, this thing, which is I call a city, actually is what, say, this vocabulary calls a settlement or a populated place. It all means the same thing, but we can represent that in our data. While an ontology does that, but it goes a little bit further. It actually starts talking about how there's classes of things and properties of things, so that our settlement then becomes something like it has a different classification. A settlement is part of a province, which is part of a state, or a settlement contains these kinds of characteristics, and it's related to people by this kind of relationship. And so you'll see some examples here of OWL, CDOC, CRM, friend of a friend. These are things that you can look up and see how they define these kind of relationships. Again, we're not going to get into them too much detail, but do know that these things are there, and these things will actually really help you with what people are doing in your field. How do they use ontologies and vocabularies? And you want to be aware of these, because you don't want to be starting to create a data model and a network and then realize that you've created your own ontology, which is against what everyone else that's studying your domain is doing. Or that or maybe a lot of people have already done a lot of thinking about how to do data modeling, and you can actually take that into your own database and your own work. So just again, to keep this in mind, these things are out there. These things are actually very useful. And they really just describe how you'll talk about your data. And when we talk about your data, how many of you start out with something like this? Go ahead and put up a thumbs up or a check if you start out most of your data work with something that is big and scary as a blank spreadsheet. Yeah, a few of you. This is the all terrifying picture, right, of a nice blank spreadsheet. And this is a data model that a lot of us are extremely used to. It's tabular data, right? This is how, I mean, again, show how many of you, this is like the first thing you've ever seen from a data course. They put a table in front of you and say, here we go. It's very familiar. We've all used them. Um, this is Excel, this is Google Sheets, it's whatever you want to use. And the basic idea behind this, you have rows and columns, right? Each row is a separate entity or separate entry. Each column is some kind of characteristic of that. So a little example here, let's just say we did something about books. And you'll see that this will be our data. We have these different books. We want to get them into a spreadsheet. How do we do that? Well, we give them an ID. Each book has a title. Each book has an author. And there's a year. This is pretty standard stuff, right? Thumbs up. This looks pretty familiar. This is kind of how you'd model maybe a book in a thing. Yeah. So it's great. It's wonderful for really basic work. We always use, in fact, a lot of stuff you'll see for if you really get into graph databases starts from these kind of spreadsheets. But there's some issues here, right? This isn't quite good enough for a lot of the work we need to do. It's not a very flexible data model. It's rows, it's columns, and you need to actually have each row has to have the same columns, even if it doesn't have, say, a data entry for it. So you'll have a lot of blanks, or you might have to start making a lot of columns that are redundant. That could be another problem. So, like, let's say you have, oh, this is a type and it's a subtype, but some rows have it, some rows don't. This becomes really a kind of a big issue. Another issue is changing things. If we go back and we say, well, we have an author, all right, well, each author is listed, and maybe the spelling changes on their name. Maybe they change their name. Maybe Bruce Wayne becomes Batman. You want to reflect that in your data, you've got to change all of that. Or you've got to make separate spreadsheets for each one of your people, which are not intrinsically linked to the other one, without doing some actual like work or some code or some shenanigans that are actually hooking up both all of your spreadsheets. So it really becomes an issue of managing a lot of different kind of data and data types. And who here links different data sheets programmatically when they're working with a spreadsheet? Very few of you. And is that a fun process on a spreadsheet to link different spreadsheets programmatically so that you can change one thing and it'll cascade to all the rest of your sheets? Not really fun. It's not really what these things were originally intended for. And so that becomes kind of an issue. How do you link different files and different tables? And so this is how they came up with the relational model. And really the idea here was we're finally going to get away from this flat file spreadsheet stuff. And there's going to be logic and there's going to be the actual file format itself. These are now going to be two different things. And so this was proposed in the 70s, embraced by the 80s. And this is the databases that we all know and love. It's schema driven, which means that you actually are creating a schema of this is how my table is related to another table. You predefine the structure of this. And what do I mean by all of this? Well, we do this through a standardized language through SQL. If any of you are working with relational databases, you've worked with SQL. And who's heard of these concepts? Keys. Not too many of you. All right. So the idea is that now instead of spreadsheets, we're going to have different kinds of tables. They're going to be related to each other through these keys. And so what are keys? Well, a primary key for any one of these new tables is a unique identifier, which is not repeated in that column. Think of it almost like a social security number for your data. Best practices is we just have like random or semi-random or sequential things that are IDs, so we know the system will never repeat them. And we want IDs that are not things like your name. They want to be just like numbers or something. So, like again, if we go to our example of Bruce Wayne and Batman, there's Bruce Wayne, Batman, the Dark Knight, the world's greatest detective. These are all different names, but they all refer to the same thing. And so we'd want to have one ID that encapsulates all of that. A foreign key is a column where the value is actually the primary key of another table. And so how this works in practice is that you can have in one table, you have your primary key identifying that row, and you can have any number of foreign key columns, but each one has one value. So if you're, say, linking tables together of, oh, here is a like pasta dish and here's the ingredients, the pasta dish itself would be your entry, and each column would then be a foreign key, just maybe something else. But this becomes, actually, you'll see an issue in a second. And so let's look at our books example. We have authors. So this would be a table, a separate freestanding table. Each author would have an ID, and each author would have a name. The ID would be the primary key. We'd have maybe a table of years, because maybe we want to say something about a year. Each year would have primary key of its value. And we'd have this books table. This is where each book has a primary key. That's what identifies it as a book. That could be like the ISSBN or something else. Each book will have a title. Now look at this. The year is the foreign key, so it links to this table. And the author is a foreign key, so it links to this table. Excuse me. And so what happens is you can make a data structure that looks like this. So you have an author, and this author, she writes a book, and you'll see that this book has an ID of 1, which is okay. This author has an ID of 1, which is also okay. Each table can have, just as long as that ID is unique to that table, it can have one ID. And this book is saying that it gets its own ID, has its own title, its year is this year, its author is Alice Smith, who's over here. This author, Bob Johnson, has written 2 books, book 2 and book 3. And you'll see that each one has, as the author, the foreign key, which is this Bob Johnson guy. Everyone sees how that works? Quick thumbs up. Great. And so this is basically how relational databases work. You have you have your tables, and each one of your tables has however many records in it. So like these authors, these are individual records, but they would be in one table, say with the years, and then you link them up by primary keys. However, so this is a pretty basic thing, but it can get a lot more complicated. Does not look fun. So this is where, let's introduce something called genre to our books, right? So this becomes a little more complicated because we need to now say each book has however many genres, each genre is cooked to these genres. How do we then represent how a book could have multiple genres or multiple authors? Because you can only have one column that has this. So you've got to have these intermediary linking tables. So this book genres one would have a book ID and a genre ID repeated for however many times each book has however many genres. So if book 1, say here, graph databases for humanities, was spatial and computer science and graph theory, then it would have to say book genres links book 1 and spatial humanities. Book genres next row is book 1 and computer science. Book genres, the row after that, would be graph theory and book 1. If you had multiple authors, you would have to say over here, book 4 has author 1, book 4 has author 2, and so on and so on. And so you can see here that in order to model these relationships, these very complex ones, you have to have these linking tables that are put in there. Now, this can start to become a really complex and really difficult issue to basically model as your stuff and as your data, as you're working with your data. Because you have to keep adding these different tables and say, oh, wait, now I've got 3 or 4 other things that can be in this value. Again, a show of hands, how many times have you guys maybe been working with, say, spreadsheets or databases where you've run into this situation? Where as you're working on it, you're like, oh, now this one thing that I thought would be one value is now three different values, and I've got to make another linking table. Yeah, see a couple of hands there. That is not a fun situation. And so this becomes a really big problem. And this is one of our big problems with the relational model, is that you really need to know the structure before you start putting in all of your work, or else you need to start creating a lot of intermediary tables on the fly, which aren't always the best idea. These are really necessary when you have complex queries, we have many to one and many to many relationships. And again, if you don't design these from the beginning, then you've got to change your data model as you go. And if we go back to this slide, well, what if you want to call genre something else? What if you decide that, computer science isn't one genre, there's actually three or four subgenres. Now I've got to go change that and make sure that my book genres one changes as well and remap everything. Maybe I change some stuff about authorships, or maybe I have, book authors, maybe I want to call that, book contributors, because I have authors, contributors, and editors, or maybe I have different roles. And you can see that these additions start cascading, creating problems. The other thing is the relational model, despite its name, is really bad about modeling relations between these tables. As you can see from our example, these become really complex. You have to start doing all kinds of joins, like, well, this table where those values are the same as this value, but not that value, et cetera, et cetera, et cetera. And it just becomes a mess. And so relational data models are great for really quick statistics, but they're not so great at modeling the connections between things. And that's really one of the important things about graph databases are connections. And a lot of the data and a lot of the research we do is around connections. And so relational models don't really accomplish that. And so to get around this, they decided to make a sequel to SQL called NoSQL. Say that 5 times fast. And what is NoSQL? NoSQL is kind of a recursive acronym. It's kind of fun. It means not only SQL, and this is really an umbrella term for databases that do not only use SQL, that do not necessarily have a fixed schema, and they might not rely on a tabular structure. And so these are things that are relatively new in comparison to relational databases, and are things that are really starting to take off, especially in big data and research worlds, as these data models need to develop and be iterative, and they need to change over time and bring in different kinds of data sources. You can't have a fixed schema for that. You've got to be making relations between what you're doing and your data source. And so that's where NoSQL comes into play. And the key part of this is that it is that flexible schema, that what you've defined as this is my data or this is how I'm structuring it can actually change without you then dramatically having to rechange everything else. All you're doing is adding or subtracting connections between things rather than making tables to facilitate that. And so there's a few main categories of NoSQL databases. And we're going to go over each one of these. There's wide column stores or column family ones. There's key value databases, document ones, and the reason we're all here today, graph databases. So a wide column store or column family database is that it's kind of like relational one in that it has rows and columns in a tabular format, but it's a little bit different. Each row does identify each record, but here's the interesting thing. The columns are grouped into families. And so you have different groupings with different rows that don't really connect in the database, but they're logically connected. And what's interesting about these is that the number of columns for each row is not fixed. So if you have a family of columns, say around our book model, you can have all the book information there, but each row doesn't have to have all of those columns. And so you don't actually have to have a bunch of nulls or null values. You're just saying that this row has any number of columns from this column family filled out with data. And so if we go back to our book thing here, we'd say that our books table has a book idea. The columns are title, author, and year. And that's all we need. That's all that we're modeling here. And so this column family, title, author, year, maybe another column family would have information about a publisher or something, but they're not linking to this one. And so these are logical groupings of columns that are freestanding, where each one of these rows can have any number of them. And just to give you some ideas about them, the schema is pretty flexible on these. There's a query language, CQL is used in Cassandra, which is one of the products. These are also absolutely horrible, as you may imagine, on relationships, because you have column families are self-contained. They're not talking to each other. And so these are really specialized ones that generally are used for things like if you have time series that somehow have some differences, if you have some logs for your system files, they might be using this kind of thing. But generally, the column family databases aren't used that much. And for a lot of, like, say, humanities work, it's almost used not at all. Another NoSQL one is key value databases. And these are actually used a lot because they're very simple. What these are is that the key is used to identify a value. So, like Chevrolet car, Ford car, that kind of thing. And this is extremely flexible because all you have are two values, a key and whatever that key means. That's it. And as you can kind of imagine, again, this is really bad at relating data items to each other, but it's extremely fast if you're just looking for, here's a key, give me the value. And so again, if you had a key and value, you'd say book is graph databases, book 2 is network, book 3 is this, and that would just be how you march down this thing. There's no schema because it's just simply key value. This is API work on this. There's absolutely no relationships unless you somehow manage them yourself or write a program for yourself. And this, again, is very specialized stuff that doesn't apply to a lot of our research areas. These are really great, again, for really high indexing, high speed, storage kind of things where there's not a lot of questions you're asking about your data as much as you're just trying to get values that have gone by. So, okay, great. Well, this one, let's talk about the document model. And this one's getting actually a little bit of traction, especially in cultural heritage applications. And it's extending the key value idea, only now it's talking about keys in documents. And the data itself is in like a JSON or vice or an XML format. And so the idea is that you have a key that refers to an actual document, which can have its own internal structure and its internal logic. And so this has actually been used a lot in, say, archival contexts, because you have your key being whatever its identifier is in the archive, and the document being the document itself. And so each document can have whatever structure or schema that it needs. So your database could actually have, again, like, here's document 1, that's a JSON file. Document 2 is an XML file. Document 3 is a JSON file that conforms to a certain ontology. Document 4 is another ontology. Doesn't matter. That's just how these things are stored. So this is actually can be a fairly useful model, but again, it's not great at linking things between documents. Because all you're really doing in this one is storing, again, a key value, key being the document, value being the key being the identifier, the value being the document itself. And you can write things where it goes and searches and then tries to look at another document for that. But again, it's not really a strength of the model. The strength here is identifying particular documents and allowing you to go down and search within them using their own logic. So it would look like something like this. You'd have books and say book 1. Here it is. You can see this is a JSON object, say the title, the author, et cetera, et cetera. But I could also throw in, say, book, a movie. I could throw in a slip of paper. I could throw in an artwork, all within the same document store. All right. I'll pause here for a moment. Is everyone following along? Any questions or anything to jump back to? All right, I'm not seeing any panicked red X's or anything, so we will continue onwards. This again being a very quick rundown of some of the stuff you can use for document databases. This is great for catalogs, user profiles. Uh, Again, they're very useful for certain contexts. But let's talk about what we want to make connections here, right? What we're interested in really for graph databases and what they are is talking about nodes, relationships, and properties. And so this is built on the network data model and the network kind of ontology. That's why I mentioned it in the beginning, is that if you're going to be using graph databases, you're really embracing this idea of nodes and edges and connectivity. You're really trying to get at what does it mean to be connected? What is that connection? You want to surface that information. You're not really looking necessarily at what the nodes are. You're looking at how they take what their relationships are. So, what is the structure of those relationships? How do those relationships define your domain? How are things brought together? That's what you're studying. And so that's something to really understand before you jump into a graph database is that you're really looking at the structure of connections much more so than the internals of the objects themselves. And why is that important? Because, well, networks are a collection of entities. Some of them are linked, and this goes through all kinds of subject domains. Networks are ubiquitous in our society. Networks are everywhere. I mean, go ahead, throw a show of hands. Who's on some kind of social network software somewhere? Nobody? Nobody's on a social network? I don't believe that for a second. Yeah, we're all on some form of social network. How many of us want to delete those social networks? But we're all on them, right? We're all on something. Think about how are you attending this workshop right now? Through an electronic network, right? Think about how do you go about your daily life? You're in a society of, again, people networking. You are in a ecological network. And you're in any number of networks that stack and on top of each other, interact with each other. That's what these things are interesting in. That's what we're trying to study. It's an extremely flexible definition of a network. And it is because we can, if we're talking about the relationships between entities and concepts, we're kind of pulling back a little bit from our domain specific interests. I'm thinking more about, again, how the structure of how they interact. That is something that's a little more universal than, say, some of the more detailed stuff that we look at. And so a very basic thing about network terms: nodes, edges, and a graph. And again, if you know this, go to a happy place for a moment, but we do need to get through this. So who's heard of a node before? A node, this is the stuff you're looking at. These are the entities of your network. These are we are nodes if we were going to make a network of UCLA. These are, nodes can have, excuse me, any number of attributes, or think of those as think of this almost as like a table. Each node is your row, and you can have as many columns and attributes and stuff describing it as you want. And they can all be different. That's one of the big strengths of the graph data model is that, let's just say that we're making a graph of all of us here, that I'm some researcher and I know information about me. I can fill out a lot of different things. I may not know anything about you other than name. I put down name. Maybe I look at the spreadsheet you filled out when you registered for this talk. Some of you filled out some data, some of you didn't. In a spreadsheet, there's all kinds of blanks. And nodes, I'm only attaching the properties that I have things for. So I don't have blanks. I don't have null values. I only have what is associated with each node. And I can, again, add to this anytime I want. I can change this anytime I want. I can completely reconfigure the attributes I use for a node, and that will not affect its position in the network. And that's, again, a real big strength of this. You can add all this additional information without actually fundamentally changing your data model. Now, if we're going to put these on a graph, these are traditionally looked like as circles. You may also see actors used for nodes. I like to use nodes simply because I think actors gives it a sense of agency that they don't necessarily have. Edges, this is what puts our nodes together. It's indicating a relationship. Sometimes these are called links. And what's really fun about network analysis, you define what this is. What is a relationship? Well, depends on what you're studying, but again, up to you. Let's go back to your example of census data. Maybe your edge is a person who lives at an address. That's your edge. The address, that's your other node. The person is the person. Maybe you have two people and you say these people are related. Well, there's an edge, a relationship. So again, anything that you want to put into that edge, you get to define what that means. This workshop, let's just say that I'm doing a network analysis for this workshop. We're all connected to me because I am the person broadcasting the workshop to you. That would be a network. These edges can have something called weight, which is an interesting concept, again, defined by you. It can be things like the number of interactions people have. It could be something like you make it the quality of interactions you have. Think if you were going to make a network of your friends, you could assign a weight for how good of a friend they are. I would never let that network out into the wild because you'd probably lose a bunch of friends if you did that. But that's the kind of thing that you can do as a researcher. You can assign weight, you can assign edges, and again, you can actually put properties into these edges, and the properties again are up to you. These are lines on a graph. And a graph is essentially the mathematical model of network structures. There's rules for it, there's math behind it. We're not going to really get into that so much, but we are going to show you how a graph database actually creates a graph. The graph being what holds your nodes and your edges together into some kind of data model and data structure. And so a graph, this is the essential basic graph. Node A is connected to node B. That's really exciting, but that's all this is. So if we were to have, let's say, our tables, this would be row A, row B, and we would say this is a connection. In this case, the direction does not matter. We don't need to put any arrows in. We don't need to make any indications. This is the default idea of a graph for most social network applications or for most graph database applications. We're just saying that there's a connection. We're not implying anything about directionality or anything. We're just saying that this is two things, they are connected. So to give an example, this is from Game of Thrones, and this is a graph showing how many times two characters are interacting in the book actually. So the more times they interact, the thicker the line. And you can see that this is not directionality. This is just people who are on the same page interacting in the story. Yeah, spoiler alert, you can see who the big people are here. So any questions on this? This is a undirected graph. These are your nodes, these are your edges, and this is the kind of structure that we'll be making. Now this is in contrast to something called symmetrical or asymmetrical edges. Well, undirected ones are symmetrical, doesn't matter. Asymmetrical or directed graphs, the direction does matter. Because sometimes you want to say A has some kind of connection or influence on B, but not the other way around. If we go back to our books, an author writes a book. A book does not write an author. So you want to indicate that in a relationship. And this is what we call a directed graph. These have directed nodes, directed edges. And spoiler alert, but you know what? It's been out, whatever. This is a graph issued by HBO, so whatever. So again, they're spoiling their own show, which shows you the relationship between people, and you can see married ones are actually undirected. It doesn't matter. Well, look at this: serves, killed, guardian, parent. These are very directional relationships. And you can see visually, you have arrows indicating how that direction goes. And so that's important when you're actually making some of these graph databases, and we'll get into some of the query language in a second, is that you do establish directionality if that's important to what you're studying. Um, Again, things like people being friends, maybe not so important. But can you think of maybe examples in your own work of where directionality is important and where directionality is not important at all? I can tell you again, for most historical things, a social network, if you're just saying that people know each other, directionality is not really an issue there. But if I'm making a family tree, yeah, unless you get into like weird paradoxical time travel, directionality of parentage actually matters. What about examples from your own work? Anyone think of any? Ah, a supervisor to reporting relationship. That's right. So there's a hierarchy there, an administrative hierarchy that you want to preserve in your network. Another example, think of a physical network. Think of one-way streets. Certain streets only connect to others going in one direction. A project to team member. Again, yes, very administrative kinds of things that you have a project that has team members working on it, not really the other way around. So just think about that. What is directionality? What does that matter to you when you're setting up graphs? And so some things to consider for our data. Again, when you start thinking about putting this into a graph database, what is your data and why do you want to make it about relationships? And just keep that in mind. Why do I want to show this as something that is relationship based rather than say tabular or that kind of thing? What are you trying to show? If you're just trying to show like, oh, these things have, there's this many of that or some quantification, maybe you don't want to bother with a graph database. If I want to show this is how these things are structured, this is how people navigate a system, then I'm probably going to want to use a graph database. How are you going to organize your data? How are you going to get things together in a way that makes sense for saying, here's a start, here's a connection, here's a stop? And why do we talk about ontologies and vocabularies? Are there standards in your field? I can tell you that for geographic modeling online, there's plenty of standards. For historical GIS, we have linked traces, linked places. We have JSON formats we have shapefile formats. We have different kinds of standards that have to be used. If we're talking about, say, ancient studies, there's the digital network ancient prosopography things. There's different kinds of coin standards. The same might be for your field. Whatever your field has, think about the ontologies. Look at how people are already structuring databases and sharing them. And you're going to want to structure your stuff the same way. So really think about what it is that you want to put into a database, and that's going to really help these next steps. So you decided that you want to show relationships. You want to dive into the world of graph databases. Well, it's not so easy. There's two main types. There's also a few other ones, like say hypergraphs, that we're not going to get into because they're still not really widely used. But the two main types that are used are RDF triple store graphs and linked property graphs. Now, I'm going to also mention Wikidata Wikibase. It's not a true graph database, but it is used like one. So let's jump into that. Who has heard of RDF and triple stores before? One of you. Yeah, this is generally where if I'm talking to, say, a historical crowd, they start to either fall asleep or run for the exits. But we'll make this MLIS student. Yes, you're probably knee deep in triple stores and RDF. I do like this stuff, but I'll make this pretty brief just so we can go over it quickly. Although, if you are an information person and you're really interested in getting your stuff out there and linking to other projects and pulling in their data, this is the backbone of the semantic web, and almost all linked open data is based on RDF triple stores. And now, what's kind of fun about graph databases is you can use linked properties, convert them to an RDF so that then they can be used for linked open data. Or you can use it natively. Again, depends kind of on your comfort level and what you want to do. But if you've heard of the semantic web, if you've heard of linked open data, RDF is what is behind all of this stuff. And it's a key technology in big data because there's so much of it out there that you're just kind of describing it. And that's what RDF really, and triple stores are really helpful. And so RDF is a data exchange standard from W3C. We're not going to get into really the details of it because you don't need to know it. But the essential idea is that it's subject, predicate, object, so that you have an entity that you're describing and you assign basically a URI or an identifier for that entity. You have a relationship to another entity. The relationship itself has a URI or some way of describing it. And the third one has, surprise, a URI or a way of describing it. And it works like this. This person wrote that book. This person being the subject, that book being the object, and wrote being the predicate. And if we were to put this into action, each one of these would actually point to something on the web or something in your database that defines each one of these terms. So you would define this person, you would define wrote, you would define that book. It would look something like this. If we go back to our book example, we'd say that graph database of the humanities, well, that would be an ID of something. We would say has an author, which would link to how are we to describe has an author. The author being Alice Smith, who would have her own entry. Then we'd have another row that this same book is published in this year, and so on. And so you can see that our RDF database sets up these very simple statements. And you can see that it's very, compared to what we're looking at for relational databases, this is fairly clean, right? You've got, here's our entities, we have our descriptions, and they're linked to each other as necessary. And so, again, to just go over the structures, triples, subject, predicate, object. They have, if you're really interested in it, look up OWL and RDFS. It gives you a lot of semantics. The query language we use for this is something called Sparkle. And again, ontologies, linked open data, semantic web. It's really used a lot for linking data and describing data. So if you're into metadata, if you're into getting your, again, putting together your data with others, RDF graph databases are something you probably really want to consider. The other one, and probably the more popular one for a lot of, say, humanities work or for people who are really looking at doing social network analysis, is linked property graphs. And these give you nodes, sometimes again called vertices or actors, and you put any number of properties on these things, and that you have a relationship. And actually, for a lot of linked property graphs, that relationship is directional. You're saying this node is related to that node, and the direction does matter. And what's fun about these is that there's no linking tables. Nodes and edges are actually primitive types. All you're saying is that this one is linked to this one, and there isn't an intermediary table. It's actually linked, as far as the computer's concerned, it understands that from each one of those nodes. So you don't ever have to generate a third table. You can just always say this item is related to that item without it having to make another step. And you can see how this is actually really flexible, because I could say, here's my database. Oh, I'm bringing in all of your data, and I'm just going to say, oh, this entry is related to that one, this entry is related to that one, so on and so forth, defining them as I go. And so, what the problem though with these is that there's no industry standard query language. There's no SQL for labeled property graphs. Now, Neo4j is currently the most popular implementation of this, what we'll be talking about today. And to give you a visual example of it, you'll see here that I have a node, an author, that who wrote a book, the book is published in, and these would be the nodes are the circles, and the arrows are my edges. And I can define these however I want. I can use a standard vocabulary if I want to, or I can actually relabel these differently every time I use them. So there isn't really a control on what I'm doing here. I can put controls and I can put restraints on there if I want, or I can just freeform this and say, I'm going to make whatever connection I feel like at that moment from this node to that node. There's no set schema here. There's no set descriptions. It's entirely up to me. And so, again, just so put this in a chart form, nodes, edges, and properties. I can have a schema or I can make it dynamic. It doesn't matter. It's that flexible. Query languages are very specific to which program you're using. The most popular one is Cypher. We'll be talking about that later. There's also Gremlin, Tinkerpop, this whole Apache one. The relationships, this is the essential thing of a graph database. It's just all about relationships. And this is really kind of interesting that you'll see some examples here. There's used a lot of social networks because you can put whatever properties you want into each node, showing however many connections, which you define however you want to define them. But they're also been used a lot in, say, like online recommendation engines, linking you to all of your little purchases. That's a little bit scarier in my opinion. What's also very interesting is the use of for fraud detection. Because if you start linking entity who spent money here, who spent money there, who spent money there, and you actually can build this network showing how people are, say, laundering money. And you can say, I want to look at the start of where this money started, and I want to look at the end. And you can see, and so it can actually show you all the steps in between, but then show you how one per entity is getting all the money, say, for all these transactions. So that's been actually one of the real world uses of graph databases, is to basically cut through a bunch of these like shell companies and shell payments to figure out who's actually getting money from whom. Wikidata and Wikibase. We've all used Wikipedia, but who's here's encountered Wikidata or Wikibase before? Has nobody used Wikibase or Wikidata? My goodness, that will be your homework. Go and explore it. Wikidata has actually become right now the largest collection of linked cultural heritage data the world has ever seen. And so think of Wikidata, Wikibase as taking Wikipedia and making all of its information into a linked database. But it's not quite a graph database. And so it's not a true graph database because it's still based on, underneath the hood is a relational database. But what it does is it uses graph-like structures to describe how things are related to each other. And so it's based on the entity relationship model, where everything, and there's an item which has properties that can connect to other items. And so, while we're there, since no one has actually seen this thing before, I'm going to actually bring one up. And so you can look at a Wikidata item. So let's go ahead and we'll just, so you can see a example of this in the real world. So here we go, Wikidata, and we'll search for UCLA. There we are. Can everyone see Wikidata on this tab? Great. And so let's go to University of California, Los Angeles, and you'll see an example of what I'm talking about for Wikidata. So here's our wonderful UCLA, and you'll see that this is its actual identifier, Q174710. So this is the item, UCLA. Underneath the item, you'll see different kinds of properties. It has English property that's knows all this stuff. But if you get down to statements, UCLA is an instance of a public research university. So this item, UCLA, has a property instance of, then what's it? It's an instance of public research university, which is defined here. And you'll see that it has another instance of public educational institution of the United States, instance of university campus, and it's an organization. Of course it is. It is part of UCL of University of California. you can see all these different properties associated with UCLA. That's kind of fun. But now maybe you're saying, wait a second, that looks a little bit familiar. It does, because the whole idea between Wikidata and Wikibase is that it's going to work with a semantic web. So all of the stuff is actually really similar to RDF. And so you'll see that, again, UCLA is a instance of a university. Well, that's a subject object predicate. And so here would be an example of, let's go to our book example of, say, graph databases for the humanities would have a author who is this person. It would have a publication year, which is this. So you'll see that it's actually structured almost exactly like an RDF graph database. It just simply under the hood is not. And so that's a little bit confusing, but it's a good example of how graph database ideas are actually influencing now relational databases. And so just to give you an idea of what we've talked about, here's the three of them. We will be putting these online, so you'll be able to reference this chart later. But I'll give you an idea of Wikibase, what a graph database, and an SQL relational database, where they're kind of similar, where they're different, and how this sums up our ideas. So, everyone with me so far, or have I lost anyone? We're all good? Right. So, because what I'll show you now is we're going to go back to, when do we want to use this graph database? Now that you know what these things are, and if we look back, this is our, again, our relational database, just to get it back into your mind of what we're coming from. Why do we not want to use this? Why do we want to use a graph database? Well, again, when we're looking at complex relationships, networks, and when our research questions are about connectivity, lineage, influence, how does the actual structure of connections work? That's why we want to grab the graph databases. And if we go back to our thing again, why do we want to do that? Well, again, this is the complex, multi-genre kind of thing. And again, a graph database will just make that so much easier. So we go from this kind of mess to, here's the same thing done as a graph. An author does the books. Each book has whatever year and linked up to whatever genres. And so you can see that I don't actually have any of these linking tables whatsoever. What do I have? Just nodes and relationships. No third intermediary kind of things. It's just directly linking the data together. And so, again, if I want to show this kind of thing, this is where the graph databases are really strong. And this would be the example of the same thing in RDF. Just simply talking about relationships and not having to make all these kinds of crazy linkages. So, but why then, why even have a graph database is what it is? Well, why do we care about making that structure intrinsic to a graph database? Well, if we're using a graph database as opposed to making all these tables and things in a relational one, we can do operations directly on the schema of the graph itself. We can actually do a lot of the network science, a lot of the network analysis natively without ever having to translate anything. And so we can, one, use constraints. I can say, give me all of the authors who have certain properties. That is a very clean, very small query in a graph database, whereas opposed to a relational database, that'd be one that would be a little more jammed up. And that'd be one that would have a lot of relations and joins. Again, my relationships can be changed without changing the structure of the database. I can add, I can subtract, I can move things around. It doesn't matter, because if I'm just doing it with one node, then it's only affecting the one node. I'm not changing the other structures. I'm not changing the other connections. I'm not changing the other properties. A graph database is also extremely useful when you're doing interdisciplinary, cross-disciplinary kind of work, where you have multiple kinds of domains and fields that you're trying to bring together. Or if you say, from an organizational standpoint, if you're bringing in multiple organizations where their structures and hierarchies might be different, all you're doing now is saying, hey, this person might be related to that person, or this person interacts with that person, and you can preserve that hierarchy or that structure. And so this becomes very useful, because you can start saying, hey, this is how we think about this concept. This is how this other group thinks about this concept. We're linked we're both related to this concept, but we define it differently. That's another way of bringing this stuff in. So I can say that, I define, go back to geography. I define a place, like say New York, as a certain boundary. You define New York as a larger boundary, metropolitan area, but we're both calling that New York. And so I can say, I link to the one, we share a concept of what a New York is, but I say my link is New York means to me this, your link is New York means to you this other thing. And the computer can actually go through and pick one of those or display them both. We know that we're both talking about the concept of New York, and we know that both of our definitions are slightly different. That is actually computational now. And that's something that the computers can take action on, and it's something that we can model. So we can actually put disagreements about our data within our data, which is something that you really can't do in a relational database. And again, one of the great things about graph databases is there are so much work on knowledge management, knowledge organization, ontologies, and vocabularies that a lot of the structure of your database you can actually pull from other projects. And again, focus on connections here. And finally, in your network, you're building a network. That's why you want to make a graph database. And the other thing is, a graph database develops with your thought process. As you work on whatever it is that you're working on, whether it's research or again, organizational modeling or whatever it is, the model evolves with your thought process, with your data that you have, with your discoveries, without breaking everything. I was just, one of the team members is on this call. We're working on actually modeling how the different kinds of music archives are structured and what does it mean to be in a song and an album. Well, does it mean this? Does it mean that? Oh, wait, what does it mean if Bob Dylan made All Along the Watchtower, but Jimi Hendrix came in and did his version? Is it a version of it? Is it an instance of it? Is it inspired by? Is it really Jimmy's song now? These are all things that you can actually, as we're developing that data model without actually breaking any of the information or the stuff we already have in there. So that's what's really powerful about this. Then the cool thing about a graph database, each node contains whatever you need, no more. You don't need to have all these kind of blank spots or null values or zeros or whatever. You just put in the properties you need. You just put in the connections you need. That's all it has to have. And again, you change this schema as you develop things. And once you get to actually sharing your data, because it's in a network graph, it's already in a network model, as we saw from, say, Wikidata and RDF, you can just basically hit a couple switches to export it out, and all gets in the way that other people can consume and use in a way that they're used to. Okay. And how do we make a graph database? Well, outputs and inputs can be different ways. You can do it from the interface. You can do this from tables. Tables are actually very popular for doing this. And you can write scripts that if you're taking your data in JSON or other structures, however you get it, you can put this into a network format. And programs like Gephi, has anyone used Gephi for network analysis? A few of you. Programs like Gephi can actually be used as inputs into graph databases with the right software, or with, say, a Python intermediary. And if you've used a Python, Quarto, there is all kinds of programs out there to actually interact with graph databases for manipulation, for visualization, for making applications. But there are some issues. There's no standard graph database querying language, and that is beyond frustrating. So unlike SQL, there isn't one standard one. It's being worked on. There's ideas out there, but it's not currently there. How many of you, if you mentioned in your field of study or your general workplace, hey, I'm using graph databases, would people actually understand what you're talking about? My guess would be not too many. I know, especially in the humanities, very few people are using graph databases. It's growing, awareness is there, but graph databases as a thing is still not that well known in a lot of areas of study. And the other issue is you do need to think of your data as a network. You need to sometimes change your thinking and think about, I'm really interested in how things are connected rather than the things themselves. And that's a conceptual step that may not be compatible with what you're actually trying to do. And the other one is we're all used to using spreadsheets at this point, or looking at data in a tabular format. It makes sense. We get it. I wouldn't say it's easy, but it's there, and it's something that we've been doing for years. Graph databases are a little bit different. There might be a steeper learning curve. These are things that you have to develop, and so that might be a barrier for people using it as well. And so we're going to try to overcome a little bit of that and look at Neo4j and Cypher. And so Cypher is the query language here, and it's used to query the Neo4j database, to interact with it, to do things with it. It's proprietary. That means Neo4j controls it, but there are open source movements to actually make the Cypher query language more of an open source kind of idea. And this language is really heavily influencing graph query language, or GQL. And it's just been one of the preliminary releases just happened. So we're hopeful that this whole situation of no standard query language will start to gel around GQL, which is being really influenced by Cypher and some other query languages. And so what we're going to do now is jump on the Neo4j sandbox. And so what should be happening is that you guys should have already signed up for the Neo4j sandbox. And if you haven't, let me drop the link here. So I'm on multiple screens. It's always trying to paste something here. So Neo4j sandbox, sandbox.neo4j.com. And I'm now going to share my screen there. And what we're going to do for this demo and this portion of the workshop is actually work with a Neo4j database sandbox. This is online. This will not hurt your computer or do anything to your computer. This is all an online application. You can blow this thing up. You can do terrible things to it. It will not matter. So just sit back, relax, have fun with this. We're going to get into a little bit of just looking at what a graph database is in the wild and how you can actually start thinking about it or using it. Neo4j does have a free version that you can use. It has some limits on it, but this will get you started. And then maybe if you like this thing, then you can jump onto it. So what we're going to do is we're going to look at the movies database, because we all like movies, right? At least before all the comic book movies took over everything. And I mean, movies are great. There's only 3 Star Wars movies. There's only 3 Indiana Jones movies. And there's only 1 Matrix movie. So let's go ahead and open up our movies database. So make sure you sign into Sandbox. You may go ahead and if you haven't registered an account, you can do it quickly through a Google account or through UCLA one. And we'll just go ahead and launch this thing. So we're going to create and download credentials. And that should just take care of everything for us. Just will take a moment. There's always the danger of doing a live database is that something will blow up. So then we hit open, and you'll see, we'll just go ahead and hit Sandbox login. And it should show up to this wonderful screen. So I'll wait a minute or two. And just go ahead and throw a thumbs up once you get to this stage. And if you have any difficulties or problems, please go ahead and ask in the chat. And once you do get to this stage, first thing we're going to do is click on this little thingy here. All right. If you were there. All right, go ahead and click on this green little thing, and you'll see. Let's go ahead and click on refresh counts, and you'll see that we have a few sections here. Excuse me. Then you'll see node labels that say that we have movies and we have person and relationship types. We'll get to all this stuff in a minute. Acted, directed, follows, produced. Then we have different property keys. So go ahead, and for the first thing you do, click on the person button. So where this says person, go ahead and click on that. And you'll see showing up here. It'll think for a little bit, and it'll show us, look at that, a graph. Nothing's connected though, and it's showing us person. And if we can click on one of these people, oh, Jack Nicholson, there you go. It'll give you the ID that he has in the database. We have a property for him, that he was born and what his name is. So does everyone have something like that? You click on person and you see this. Now, that's all fine and good. But let's look at what's happening here because it shows us a query on the top. And you'll see that it says match in person return in limit 25. Now, this is basically the syntax of a Cypher query. And so a node is enclosed in parentheses. So we're saying match, which means we want to match a certain kind of pattern. That pattern is, in this case, n is our variable. It can be anything. So let's go ahead and change that to person result. And then say return person result. What do you think is going to happen if we hit run? The same thing. Right, the same thing because all this is whatever we want to call it. We're saying whatever this variable is from, oh, here's person, and we know that person's over here. That's one of our node labels. And we want to then, so we're saying grab from person, we're calling it person result, and we can limit that later, but we'll get to that in a second. We want to return that variable, and we want to limit it to 25. Go ahead and take out that limit and now run it. That's 133 people in the database. And so see that they all kind of pop in. Oh, there's Gary Fisher. That's cool. And you can zoom in. Oh, whoops. I'm holding down command there. Then you can zoom in. And what's fun about this browsing interface is that go ahead, click over those nodes, and click on this bottom gray thing. That'll bring up everything that is connected to that node. And so I've now clicked on Mike Nicholas, and he has, you'll see, if we look at him, we see that he has directed this movie, The Birdcage. He has also directed Charlie Wilson's War. You can do that's like Ice-T. We can click on that, and you'll see all of the connections to the database. We have Ice-T acting in Johnny Mnemonic. Everyone following that so far? Okay. So if you're following that so far, we can also say, then go ahead and put into the chat, how would you load movies into the variable M? So if you're going to do this kind of thing, how would you do this for returning movies? And we'll say movies being, we'll call it M. So I would do match. Go ahead and throw in a guess. How would someone put in the chat? How would you do this? Do you think? The question being, again, I'll put that question in the chat. No thoughts? I would say match M. You can see that there it auto suggests movie. And I can say return M, and that will give me my movies. Now we can do something else here. I can say match. Let me see if I remember how to do this offhand. Movie where, let's say, a property. Let's just look at one of our movies here. We're released, all right? Where M dot released. Let's say we only want movies that were made greater than, say, 1990. Oh, 1999. If we run that, what just happened? So look at the query. I'll put it in the chat so you can try it out again. What's going on with that query? Right, all the movies. So what we're doing there is we're saying, we'll look at the language again. We're saying match, grab from into the variable M, everything for movie. But now I'm saying where my property in M dot released, was greater than 1999. And if I would do something like greater than 1995, we'll see now there's 27 nodes. And so this is how you would structure that kind of query. And you can see how quickly you can see these kind of things. Now, another thing that we want to look for is that relationships are enclosed in square brackets. And it's the same kind of idea. And I'll put this in the chat here, that relationships are expressed like this. And so they say, oh, somebody works for something, or somebody is, well, in this case, like we would say, maybe directed something. And so what you do then is you can say that we want to match a person who has a role. And so let's look at an example here. Hold on one second while I bring it back up, because it just fled my screen because of course it did. Of say, let's say we want to find all the movies that somebody directed. And so if we go and we look at our query here, I'll put this in and I'll put this in the chat. So let's look at the structure of this thing. Now I'm saying that I want to match, again, loading all the people into P. And here we go, connected, that's how you do a connection, where directed, so I want to grab all the direct relationships into D. And so where a person is connected to by a relationship directed to all the movie nodes, where any movie released after 2010. And I want to return the person, I want to return the relationship, and I want to return the movie. So everyone sees how that works. I'm matching my loading all my people into P. I'm saying that person is connected to this directed by a relationship, which is then connected to a movie. I could just as easily say acted in or produced or reviewed, but we're just going to say these people directed it. If we run that, you'll see the output is, in this database, we have the Wachowski sisters who directed Cloud Atlas, along with Tom. So you'll see that this query grabbed all the people who are connected to this directed edge, where that directed edge is connected to a movie where that movie was released greater than 2010. And that was done in this little line of code. For those of you who do spreadsheets, how much work would you have to do to get that same kind of result from a spreadsheet? A little bit more work. It's a little bit more complicated, but you can see how you can do that here. Everyone following along with this so far? Right, great. And then another thing that we can do, can someone type a query to get all the people who acted in a movie that was released after, say, after the year 2000? Then I'll put that in the chat. Does anyone take a shot at that one? All right. So let's see what happens. We put that in. So we're saying that you're matching, you're getting a person for P connected by this acted in, which we're going to say is D, in a movie, M, where the release of the movie is greater than 2000 and P, D, and M. And there you go. That's your little web of connections. And what's interesting about this is you can start seeing, hey, some of the same people are connected through movies and directors. There's this, what we call this a giant component in network terms of all these connected people. And we've got a couple other disconnected components out here related to, well, was Werner Herzog, Orsky Dawn, and Frost and Nixon. But these other movies, Charlie Wilson's War, Cloud Atlas, Matrix Revolutions, Polar Express, all these are linked by one actor or one director or something like that. So there you go. That's pulling all of that. Now, here's something that's kind of interesting. What do you think the difference is between these queries? If we're going to put in this as opposed to this. So I'll put those in here as well. Our first one is this one. As you know what that one is, right? We're going to bring in people, returning people, limited 20, so just 20 people show up. What happens if we do this one? What do you think is going to happen in this query? All the nulls. Why do you think null? The N for null, right? Well, not in this case. In this case, it is N for node. Go figure. So we're saying here match anything and return anything with a limit of 20. So just grab 20 nodes and return them. I don't care what they are. I don't care what the properties are. I want 20 things on this piece of paper. So how would we grab then, say, every node to display? What if we just do, instead of a limit, return them all? Ah, look at that. There, all I did was remove the limit and said, return every node I have in my database. And I've got this wonderful, massively connected component. So that's one way of showing every node that you have in your database. Now here's something interesting too. We're using match. Match assumes that the node of the specified query exists. But then we have this other thing called merge. Merge adds the node if it does not. So let's go ahead and run this query. Go ahead and run this. We're matching from the node's person where their name is John Doe, and we want to set a property, person status is found. What happens if we run this query? Look at that. No changes, no records. Because I'm using match, and because nothing matches it, it returns nothing. But if I want to say, let me rerun this query with the idea of if there isn't a person, create them. And so that is where I'd run, instead of match, this thing called merge. I'm going to say merge this person, and you'll see here that I'm using JSON notation. If any of you know JSON, this is what it looks like. That's my property name. Name has the value of John Doe. And I'm saying on match. So you can see merge means find them. If they don't find them, create them. Once they're created, I'm saying, oh, you've created it. Now match it. And on the match of finding that person, set their status to found and then return the person. And if I run that, you'll see that I've now created John Doe. He's now part of my database, and he has an ID. He is ready to go. And so that's how you would add more people. And you can see he's not connected to anyone. He's just there. Now you'll also see that the person's status didn't get set because that on match needs to actually be a little bit different. So if I go back here and I say now match the person, and let me put that up here. John Doe, the person's status is found. Let me go ahead and hit that, and you'll now see I've added that. So I've got to create the person first. This part would not work there until I've actually matched him directly. So that just shows you an error that actually pops up a lot because people will say, oh, I found them. Now I'm going to match them. No, you've got to merge them first. Then your next step is match them. That's just something that will come through use. And how you can create a relationship, this is the one that I'll leave you with in terms of a querying, is now I want to make a relationship in my database, right? And so let's just go ahead and I'll show you how that works. Here we're saying I want to match a person and a movie. I want to say the name of the person is Tom Hanks and the title is Cloud Atlas. And I'm creating this relationship of P connected to watched to M. Does everyone see how this is working? I'm matching, again, person and movie, filtering it to where P is going to be Tom Hanks and M titles Cloud Atlas. And so saying, all right, once you have that person, create a connection. So person, where there's our connection key, using our relationship type, which is W watched, and you'll notice that now it's directional, that person is watching a movie. And then I would return the type of W. So go ahead and run that. And you'll see that the type is watched. So if I was to match, let's go ahead and pull up our person. And we can just do this. And we'll say we're p.name equals Tom Hanks. We will see. Oops. I messed something up there. This is the problem of always live coding on a demo because you can make a typo. Where did I mess this up? Oh, what does anyone see what I forgot to put in here? I would say extra credit. Yes, a return. Return P. I would give you extra credit or a candy bar. So there we are. I forgot the return statement. See? So there's Tom Hanks. And you'll see that I haven't done any properties. But if I hit his little connections here, you'll now see that he watched. See how that got added? That's what we just put in. And you'll see that there are now multiple relationships connecting him to Cloud Atlas. And that's something that you can use, and that's something that you can model in a graph database. I can say he acted in this, he watched this. I can say maybe he produced this, maybe he did something else with that. Maybe he marketed it. And you can see all these different relationships you can add to two nodes where before you'd have to add table upon table upon table. And so I just want to leave you with that this is, again, a very high level view of graph databases and a little bit of querying just to give you an idea of how they work. But I hope that you have at least enough to get started, at least enough to jump in, and to actually just start working with these things, thinking about whether or not graph databases are appropriate to the work that you're doing. So with that, we're going to end the recorded portion of this. And if you have any questions or any issues, I'll stay on. So again, thank you for your day after the big game for spending your time with graph databases. And we'll now jump into questions and answers.